Hi friends, welcome back to Electrical Online channel. In the previous week, as a part of the 500 subscribers celebration, we explored the master list of electrical laws and theorems, your ultimate reference guide. Today, we dive deeper into that list, focusing on some of the most important laws and network theorems. These laws are the foundation of all electrical engineering and competitive exams. But not just the definitions, I'll give you simple formulas, real-world examples, and uses. Let's dive deep by category-wise. In that first one, basic circuit laws. Ohm's law. Definition. It says that at constant temperature, the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance. If resistance stays constant, increasing voltage will increase current. It's the foundation of all circuit analysis. Formula. V equals I times R. Example. Imagine water flowing through a pipe. Voltage equals pressure pushing the water. Resistance equals narrowness of the pipe. Current equals flow rate of water. More pressure means more flow. Narrower pipe means less flow. Uses. To calculate how much current flows, how much resistance to use in a circuit, and designing all basic electrical circuits. Kirchhoff current law, KCL. Definition. At any junction in an electric circuit, the sum of currents entering the junction equals the sum of currents leaving the junction. It's based on the conservation of electric charge. Charges don't vanish. Formula. Sigma I in equals sigma I out. Example. Think of a traffic circle. If 5 cars enter, 5 must leave. If 3 enter and 2 leave, 1 car is stuck. Current behaves the same, nothing disappears. Uses. Used in nodal analysis and current distribution in parallel circuits. Kirchhoff voltage law, KVL. Definition. The total voltage around any closed circuit loop is zero. That means the energy supplied, battery, is used up in resistors, bulbs, etc. Energy is conserved. Formula. Sigma V equals 0. Example. Climbing upstairs, plus V voltage, then coming back down, minus V voltage, equals you're back where you started. Same with electric loops, sum of rises equals sum of drops. Uses. Used to find unknown voltages in mesh analysis. Second one is electromagnetic laws. Faraday's law of electromagnetic induction. Definition. Whenever magnetic flux linked with a coil changes, an EMF, voltage, is induced. Faster the change, stronger the voltage. This is how generators work, by moving magnets or coils. Formula. E equals minus N d phi / dt. Example. Move a magnet near a wire and you get current. Like shaking a cola bottle creates pressure, moving magnets create voltage. Uses. Used in generators, transformers, and induction cooking. Lenz's law. Definition. Nature doesn't like sudden changes. Lenz's law says that the induced current always opposes the change that caused it. The minus sign in Faraday's law is because of this. Formula. E equals minus N d phi / dt. Example. Try to push a magnet into a coil, it pushes back. The coil resists change, like your brain resists sudden cold water. Uses. Used in braking systems of trains, eddy current braking, induction motors. Ampere's circuital law. Definition. The magnetic field around a closed loop is proportional to the electric current flowing through the loop. It connects current and magnetic field in circular paths. Formula. Conterintegral B times dl equals mu times I. Example. Like swirling water around your finger, more current, your finger speed, more swirl, magnetic field. Uses. Used to calculate magnetic fields in wires, solenoids, and coils. Biot-Savart law. Definition. It explains how a small element of current-carrying wire creates a magnetic field around it. It shows the direction and strength of the magnetic field due to the moving charges. Formula. dB equals mu / 4 pi times I times dl times sin theta / r square. Example. Like perfume spray, the closer you are to the spray wire, the stronger the smell field. Uses. Used in magnetic field calculation of loops, circular coils, and wires. Next, third one is electrostatics laws. Coulomb's law. Definition. Electric charges attract or repel each other with a force proportional to their charges and inversely proportional to the square of the distance between them. Formula. F equals K times Q1 times Q2 R square. Example. Imagine two balloons rubbed with cloth. Now, place them close, they push each other away strongly. Move them far apart, the push becomes so weak, it's like they forgot about each other. Uses. Used to calculate forces between charges in electrostatics. Gauss law. Definition. The total electric flux through a closed surface is equal to the charge enclosed divided by the permittivity of free space. It simplifies complex charge calculations. Formula. Phi E equals Q inside / epsilon 0. Example. Like air pressure in a balloon depends on how much air, charge, is inside. Uses. Used in capacitor design, electric field calculation in symmetrical charge distributions. Next, fourth one is energy and components. Joule's law. Definition. The heat produced in a conductor is directly proportional to the square of the current, the resistance, and the time for which current flows. Formula. H equals I square R times T. Example. Phone charger gets warm, that's Joule's law working. More current equals more heat. Uses. Used in heater design, fuse selection, and power loss calculations. Capacitance law. Definition. The charge stored in a capacitor is proportional to the voltage across it. Capacitors store electrical energy in an electric field. Formula. Q equals C times V. Example. Like a water tank with rubber walls, voltage is water pressure, charge is water volume. Uses. Used in filters, timers, signal smoothing. Inductance law. Definition. The induced EMF in an inductor is proportional to the rate of change of current through it. Inductors resist sudden changes in current. Formula. VL equals L times D/dt. Example. Like trying to push a heavy door, it resists sudden force. Uses. Used in transformers, motors, and energy storage in magnetic fields. Next, fifth one is advanced laws. Maxwell's equations. Maxwell's equations are four laws that explain how electric and magnetic fields are created and interact. They combine electrostatics, magnetism, and electromagnetic waves into one unified theory. Gauss law for electricity. Definition. Electric charges create electric fields. Formula. Conterintegral E times dA equals Q/epsilon 0. Example. Imagine a balloon. If you put charge inside, the electric air field comes out through the balloon's surface. Uses. Finding electric fields around charged objects. Designing capacitors. Gauss law for magnetism. Definition. Magnetic monopoles don't exist. Magnetic field lines always form loops. Formula. Conterintegral B times dA equals 0. Example. Cut a magnet in half, you still get north and south poles, never just one. Uses. Magnetic field mapping in motors and generators. Designing magnetic shielding. Faraday's law of induction. Definition. A changing magnetic field creates an electric field, induces voltage. Formula. Conterintegral E times dL equals minus d phi b/dt. Example. Moving a magnet in a coil is like pumping water into a pipe. The faster you move, the more voltage is generated. Uses. Power generation, generators. Induction cooktops. Ampere, Maxwell law. Definition. Electric currents and changing electric fields create magnetic fields. Formula. Conterintegral B times dL equals mu0 I plus, epsilon 0, d phi e, slash dt. Example. Current in a wire makes a magnetic circle, like ripples in water. Even a changing electric field can do the same. Uses. Designing electromagnets. Understanding radio wave transmission. Lorentz force law. Definition. A charged particle in electric and magnetic fields experiences a force. This law combines both fields to describe the total force on the charge. Formula. F equals Q, E plus, V times B. Example. Like a boat pulled by wind, E, and pushed by water current, B. Combined force moves it. Uses. Used in cyclotrons, mass spectrometers, and electric motors. Last and final one is network theorems. Thevenin's theorem. Definition. Any complex linear circuit with multiple voltage/current sources and resistances can be replaced by a single voltage source, VTH, in series with a single resistance, RTH, when viewed from the load terminals. Formula. VTH equals open circuit voltage. RTH equals equivalent resistance with sources replaced by internal resistance. Example. Think of Thevenin's theorem like packing your entire messy room into one single box. Instead of handling 10 things, chairs, clothes, etc., you just carry one box to move it. Similarly, we shrink a complex circuit into one voltage source, plus one resistor for simplicity. Uses. Simplifies analysis of complex circuits. Makes load change calculations easy. Norton's theorem. Definition. Any complex linear network can be replaced with a single current source, IN, in parallel with a single resistance, RN. Formula. IN equals short circuit current. RN equals RTH. Example. Imagine a water tank with a constant leak speed, current, feeding into a pipe network. The leak rate is your current source, and the pipe thickness is your parallel resistance. Just like the tank plus pipe combo represents the whole system, Norton's theorem packs your messy network into one current source plus one resistor. Uses. Ideal for circuits where current behavior is more important than voltage. Useful in analyzing parallel circuits. Superposition theorem. Definition. In a linear circuit with multiple independent sources, the response, voltage or current, in any element is the sum of the responses caused by each source acting alone, with all other sources replaced by their internal impedances. Formula. Total response. Equals response from source 1 plus source 2. Example. Think of a music band. You listen to each instrument separately while they practice, mute others, and then when they all play together, the final song is the sum of all sounds. That's exactly how superposition works. Uses. Helps understand individual source contributions. Common in communication systems and AC analysis. Maximum power transfer theorem. Definition. A load will receive maximum possible power from a source when the load resistance RL is equal to the source's internal resistance RS, for DC, or equal to the magnitude of source impedance, for AC. Formula. RL equals RS, DC. RL equals ZS, AC. P max equals V square / 4 RS. Example. Imagine pushing a swing. If you push too hard, the swing jerks. If too soft, it barely moves. The perfect push strength gives the maximum swing height. Similarly, matching load and source resistances gives maximum power. Uses. Audio system impedance matching. Wireless communication transmitter, receiver design. Reciprocity theorem. Definition. In a linear, bilateral network, if a voltage source is applied at one point and the current is measured at another, then swapping the positions of the source and measurement point will produce the same current. Formula. IAB, source at A, measure at B, equals IBA, source at B, measure at A. Example. Think of talking through a paper cup telephone. If you talk from cup A and listen at cup B, you'll hear the same as talking from cup B and listening at cup A, as long as the string is tight and conditions are the same. Uses. Helpful in antenna testing and RF systems. Validates network symmetry. Compensation theorem. Definition. The change in current due to a change in impedance can be calculated by replacing the element with a voltage source equal to the drop across it. Formula. No single fixed form, based on KVL/KCL application. Example. Like swapping a road section with a toll gate, traffic change is predictable. Uses. Fault location and sensitivity analysis. Millman's theorem. Definition. Voltages of multiple parallel branches can be combined into one equivalent voltage and resistance. Formula. VEQ equals sigma VI/RI divided by sigma 1/RI. Example. Like mixing juices of different sweetness, the final taste is the average based on quantity. Uses. Parallel voltage source simplification and power distribution networks. And that's it, folks. You've just completed the full power-packed session of the top electrical laws you must know, whether you're a student, technician, or engineer. I hope the examples made each law stick in your memory. If you found this valuable, smash the like button, share this with your study group, and most importantly, subscribe for more super simple electrical content. This is just the beginning. Thank you again for helping me reach 500 subscribers. Until next time. Keep learning, stay charged, and power your future.